And Lou, who's signing his life away.
I already signed it, so I'm not sure why I want to sign it again.
And he's going to talk about collider phenomenology of string and M theory.
Okay, I'm not sure how to go to full screen, so I go like this.
Control-L.
This is Firefox. No. Okay. Let me. So, as I'm setting up the timer, I want to thank the organizer for this great workshop and give me the opportunity to talk here. My talk will be about the phenomenology of string theory and M theory at the LHC. Okay, so this is a pretty boring cartoon of the LHC, and you have proton colliders in between. And in order to make interesting phenomenology predictions, you want string theory. And in principle, everything can be done in string theory if you are smart enough to calculate everything. As Bobby already showed in one of the toy model, you can calculate the M3 halves as a function of some discrete number, basically represent the rank of the group. And you can calculate the whole spectrum, but we are not so smart enough to find the right model, to find the right manifold or compactification for the real world yet. So we have to use some information from cosmology. And after you combine the cosmology and the string theory information, you arrive with, assuming the low energy, if the low energy spectrum is MSSM, you'll have a pretty good idea about what the spectrum looks like. So I'm gonna basically review all of this and then talk about a little bit about the phenomenology on the outer side of the ring. So string theory, the first clue we get in string theory is the moduli mass bond. So Bobby already explained this in great detail. You basically write down the moduli mass matrix and pick a Scodino direction, and you can arrive a sort of inequality expression like this. And the useful result, the useful information we can extract from this is that the M3 halves should be order 1 of the lightest moduli. And this is information from string theory. And now we can combine this with the information from cosmology, because there's a famous cosmology moduli problem in cosmology, namely the moduli have a really long lifetime. And when the lifetime is, if the lifetime is too long, it will decay during the BBN, Big Bang nucleosynthesis, and really screwed up the whole generation of light elements. So in order to avoid that, you want the reheat temperature to be at least larger than 5 MeV. To make everything safe, you probably want 40 MeV. This automatically makes sure the moduli, the lightest moduli should be of order 30 TeV. Because we already know in the string theory part, M3 halves is more or less the same order as the lightest moduli, so M3 halves should also be 30 TeV. And this basically fixes all the scalar masses, and the trilinear coupling should be also 30 TeV or 50 TeV order. In order for the whole framework to work, the moduli decay will produce dark matter. To get the right relic density, you also want the suppressed gaugino masses. And this is actually the second thing we can learn from string theory. Here I'm sort of focused on G2 examples because the expression is concrete and we can make interesting predictions. So in G2, you have the tree-level correction, tree-level contribution to the gaugino mass. Here, this eta is a special correction from string theory. Basically, you calculate the correction for the KK modes. In principle, you can calculate it if you have a G2 manifold. But in this here, we do not really have an example for G2, so we just treat this eta as a free parameter. And another thing you want to notice is this P effective. It's a suppression of the gaugino masses. So gaugino mass is proportional to M3 halves, that's everything else, but it was suppressed by this P effective by a factor of 60. Because this is suppression, the anomaly part of the gaugino mass is actually important. So you can see well, it's also proportional to M3 halves, and after you combine the tree-level contribution and the anomaly contribution, you get, in some parameter space, well, I mean, with some particular choice of M3 halves and eta, you will have Wiener LSP. And you just hear from Piyush, there is a very interesting gamma line bump at the from Fermi data. Haven't been confirmed by the official Fermi collaboration yet, but many people already have confirmed and reconfirmed the result. So if you believe this gamma line is because of the LSP, then the dominant contribution will be from the Z gamma line. And the Z gamma line will tell you the window you need to produce this 130 GeV gamma line will be 140 GeV we know LSP. And this is not all the information we can extract from this result, because we have a concrete result, we have a concrete expression for all the gauge masses. We can actually calculate not only the Guino mass, but also have constraint on the Guino mass and Bino mass. So this is a graph I made. You can see we fixed the Guino mass to be 145 GeV, and the Bino mass will go like this, and the Guino mass has a slightly larger uncertainty. This I picked mu less than 0 in Piyush's graph. So there should be two branches depending on what kind of mu you are choosing. And the interesting thing you can see is, first of all, you will not get Guino LSP at 145 GeV when your M3 halves is less than 55 GeV. So in order, this actually put a stronger bond on the gravitational mass, because if you believe 145 Guino LSP. And the other thing you see is the gaugino mass, the Guino mass is actually pretty safe here. You have 900 GeV, and the current LHC limit is more like 800 GeV. And finally, the thing a feature you notice here is the Bino is not that far away from Guino. Actually, if you really want to go to the limit, here the Bino is almost degenerate with Guino. So this will have some effect when we study the Guino decay channels. So we are combining all I have said. We have the scalar masses, it's proportional to MC halves and 50 TeV, and the Guino mass suppressed. We can have this is a typical feature of the spectrum. Gordy already talked about the Higgs mass, and Piyush just talked about the 145 GeV Guino LSP. And in this talk, I'm gonna first talk about the Guino mass, the Guino search, because this is sort of the lightest color charged particle you can see at the LHC. And then because this particular feature in G2, you have a Guino LSP, and the Guino LSP makes the chargino really degenerate with the LSP. So the delta M is only like 160 MeV. So this will make the chargino will have a really long lifetime. Well, not that long, but we'll leave a track in the detector. So the first thing I'm going to talk about is Guino. So as I already mentioned, you can either use the argument of moduli stabilization to make scalars heavy, to argue that scalar should be heavy, or you can say because you believe 145 GeV Guino scalar should be heavy, you should focus on Guino at the LHC search. The Guino decay will go through off-shell squark, and because squarks are so heavy, you can make it the effective coupling, and this coupling will be inversely proportional to squark mass square. So that means the branching ratio the decay of the Guino will strongly prefer the lightest squark. And if you remember the spectrum I just showed, the lightest squark is a stop. So this is a typical decay. Well, it's a very interesting decay mode when the Guino pair production, and Gordy and Bobby and Ben already showed this graph a few times. So you have a Guino pair produced and decay to 4 tops. This gives you large missing energy, large B jets, and large leptons. But I want to remind you, it's also possible to decay to BB bar and also TB bar when you have a Guino LSP. Actually, when you have Guino LSP, it's the TB bar branching fraction is more like 70%. So it's the dominant decay channel is a TB bar. So using this feature, you can have all kind of searching channels. In principle, I should show the discovery potential for 20 inverse bar ATV, but it will take infinite amount of time to update this graph. So I show you the outdated graph for 1 inverse bar, but the general feature is the same. The most promising channel will be 1 lepton 4B. if you have TD bar, here I assuming TD bar branching ratio is 100%, you will have some strong bond from the same sign dilepton. But if you have TD bar branching fraction is not 100%, then still you get a lot strong bond from one lepton 4b, but the same sign dilepton will be not so good. This is a typical graph for we know LSP. Basically, you won't get anything from same sign dilepton, and you will have some at the one lepton 4b. Okay, so this is a Guino search, and the last thing I'm going to talk about is the disappearing chargino tracks. So this is because you have this particular pattern of we know LSP, and the mass is so degenerated, the chargino will have a really long lifetime. The decay mode is you have a chargino decay to a pair of pion, and then you get a LSP. So if you plug in the formula, remember delta M is 160 MeV. The lifetime you get C tau is 5 centimeter, and beta gamma is 2. So you will have chargino on average will travel like 10 centimeter in your detector. But because it's an exponential decay, if you require chargino to go beyond 40 centimeter, it will have 2% of the chargino produced will go that long. The reason we picked the 40 centimeter, the magical number, is because the detector structure, here you can see this is the structure of the atlas, and here you have the pixel detector and SCT. So this is the only part we're concerned about. The third layer of the SCT is like 44 centimeter. So our assumption is when the chargino has long enough lifetime to hit 3 pixel detector and 3 layers of SCT, you have enough information to construct the track. So this is exponential decay of the chargino when I simulated with ATV energy and 20 inverse Fenobar with the 850 GeV Guino. So you can see beyond 40 centimeter, you will have about 100 chargino events. This is purely Guino decay. So the thing I did is pair production of Guino and then the Guino decay to charginos. But in the case when your Guino is too heavy, you can use the other channel, namely the electron weak production of chargino. And then because the cross section is so huge, you can pay the price to get a monojet tagging on this event and still get pretty much the same number of events after you apply the cuts. And if your Guino is like a 1.5 TeV, then probably the electron weak production is a more useful channel. And the last thing I want to mention is this is a very interesting signal, and in principle, there's no physical or standard model process to mimic this. But there is the thing we haven't expected when we write the paper is because there is a large background from detector. The detector is not a perfect machine, so when along with the real tracks, you will have some fake tracks, and it's really, really difficult to study them without doing the really, really time-consuming full simulation of the detector. So I just used the result from Atlas collaboration. They already find 185 events at 1 inverse Fenobar. So okay, they already find 1 inverse. So there is a huge background. We can only hope the experimentalists will improve their understanding of the detector that will reduce the background and eventually make this a useful channel to find charginos. So this is my summary, and you could have from general consideration of string theory, you have heavy scalars, suppressed gaugino masses, and we know SP. And there is some interesting phenomenology. Gordy talked about Higgs, and Piyush talked about the gamma line. And I talked about there is also the Guino search and disappearing chargino track. Thank you.
Any questions? If not, I have one comment. Okay. There are always backgrounds. Let's thank Ran again.